originating. Alright, there we go. Sorry about that, everyone. I realized that was annoying. Okay, now I guess we can get started. As to why I look a little bit orange, the reason is because I'm doing green screening on the cheap, and my green screen isn't technically green, it's sort of a turquoise blue. It's a bedsheet I have taped to the wall behind me, and when it's not right in the middle of the visual range, and it's a little bit off to one edge of the visible light spectrum, when you cut that color out, it has the effect of emphasizing the other end of the color spectrum, so things look a bit redder than they really are, because I'm cutting out some of the blue. That's basically why I look orangey. Anyway, I was all excited about this before, but then today, starting about noon, I started feeling a little bit ill, so I don't know how long I'll go today, but I'll try and get through as much of this as I can. I'm starting to feel a little sick to my stomach, so we'll see how that goes. But it appears we have some people in the chat. People have showed up. So, let us get started. As the announcement made, what my plan is here is to do sort of a mixture of a little bit of tutorial and a little bit of sort of exploratory playing around with the audience. I had done some testing over the weekend to make some scripts that work, but when I got to the very end of it, I have a few math problems where the script isn't as accurate as it needs to be. And when I got to today, where I was going to work on it again and I started feeling a little not up to it, I decided that what I should probably do is just wait, show you what I have so far, and then if there's time permitting at the end, we can actually do some interactive work on it and have the audience actually participate a bit, depending on how I feel at the end of the bit that I've already done. So, here I have a game already saved, in which I've already gotten the ship into orbit to begin the test. The test, come on, let me click on it, there we go, is to simulate a bit of a rescue mission. So here we have this craft called Tilsa Adrift, which looks a lot like it looks when you get oh, hello, Space is Hard. Looks a lot like what you get when you do one of these missions in which someone is stranded in orbit in just one part, just the capsule by itself, and you have to go try to rescue them and come back. So, this is the test, and this is, I put this up into orbit earlier. It had decouplers on either end and some separatrons so that I could decouple the pieces that put it up there and deorbit them automatically, so that this looks very much like what a contract would look like, even though I'm running this from sandbox mode, so we can keep redoing it over and over again as we try and make this work. So that is this line out here in a really eccentric orbit, very large, and also an inclined orbit, as you can see. So I tried to set this up to make it hard, basically, not just a simple circular orbit. Then this over here, that I've called Rescue Ranger, is my ship that's going to go get them. It has an empty command pod to go get the person, a probe core, and a KOS unit. And it's in an orbit that in the beginning isn't anything remotely like this orbit, other than the fact that they are at least both vaguely counterclockwise. So this is the starting position, and I have this in a saved game that I can keep going back to and bringing up again as we keep retesting this if things don't work. So, as we're looking at this, here is my plan for the scripts that I've written. As you can see, there are several problems that would need to be solved in order to do this particular rendezvous. The first problem is that there's actually no intersecting points whatsoever. This inner orbit is entirely contained inside the target orbit. There's absolutely no crossing over points. That's one problem. Another problem, oh look, everyone's talking about the contest from the Reddit. Anyway, the second problem is that the inclinations aren't the same at all. And then the third problem, of course, is once you correct the inclination, and once you get the orbits to kiss against each other so there's a common point, then go to that common point and burn at the common point until the timing is right that you'll meet your target at that spot again. So that's the basic battle plan, as it were. And I'm actually going to do it in the following order. First, get the inclination corrected. Second, enlarge this until I detect that there is a crossing point somewhere, which will end up being over here, probably. And then third, go to the point where the crossing occurs and burn prograde, making my orbit bigger and bigger until it detects that the timing is right to get it to come back to that spot at one of the times that my target will be at that spot. Can I reduce the game audio a bit? Sure, actually. Let me just do that right now. Mostly it's reduce the music, and a little bit of the sound effects too while we're at it. Okay, that should be fine. Where was I? I got interrupted by talking about the volume. Sorry, I completely derailed my train of thought because I went to look at the volume. But yeah, the intent is, oftentimes I found when playing career mode and hard mode that I would get the missions to try to do rescues long before I've spent the money to upgrade my tracking center. So the idea is to do this whole thing without the aid of tracking center. Now, of course, I'm doing this in sandbox mode, which means, of course, I can use the tracking center to get my orbit predictions to work right. There, my mic is on now. I had to cough for a moment, so I muted the mic, and then after I coughed, I hit the mute button again, but apparently it didn't unmute. HVAC, it's not Chromecast. I had the mic muted because I had to cough, and when I hit the button to unmute it, it apparently didn't pick that up, and it left it muted. Okay. So, I don't remember where my mic muted and cut off, but quick re-summary. I'm doing this without the aid of Tracking Center. I'll have the Tracking Center turned on so we can watch, but the script itself will not use the Tracking Center at all. It's doing this all on its own. And we've all done this kind of rendezvous mission before by hand. And when we do it by hand, the basic steps are get our own orbit to the point where it crosses over the target orbit. And typically you want to do it at the higher crossing point, because it'll take a little less DV at that spot. So wait until you're right here, roughly, and then burn in a direction that'll tilt this orbit to match the inclination. And since this orbit is going this way, and we want it to be going down a little bit, that means we'll be burning vaguely south-ish. And what people will typically do if they're playing it by hand manually and not using a maneuver node is get to that spot, burn at the purple normal marker, or is that anti-normal? I forget which one is south. But burn it at the normal marker, and then keep it glued to the marker as it slowly rotates and the marker moves. Keep the shuttle, or keep the craft pointed at that as it turns. Now that's actually slightly less efficient than finding the point that's exactly halfway between the two angles and burning there and holding it straight at that point, so that your orbit gets bigger and then gets smaller back to the same size again. That's actually more efficient for a variety of reasons. And what I'm going to be doing is working through the math that actually, first of all, finds where on Earth to do the burn, and then how to aim the burn, and how to get that to work. So that'll be step one, inclination correction. So let's go in here and start doing this. First off, I think given the rate at which things will get done, it's probably quicker if I start from the script that I have already made. So if you just pardon me for a second, I am going to just copy my already made script in. automatic swapping is also not working. There we go, that's better. So, I've actually already written code to get up to a certain point. I had debated the idea that maybe what I should do is just compose it in front of you as you all watch, but as I thought about it, that's going to take probably a bit of time. So, I'm just going to start from the scripts I've already written. I think that's quicker. So first off, I have consts, which is nothing more than a standard library I've been using for ages that does nothing more than set a few global variables to some useful values. I really don't like the syntax of saying constant parenthesis colon value. It's been that way for ages. I don't particularly care for it, so I just set those to some variables ahead of time. And big num is not quite infinity, but big. Near zero is not quite zero, but or not quite negative infinity, but or not quite zero, but very close to it. Sorry about the coughing. This is just because I sometimes need to use those to avoid using infinity. Okay, so that is fairly simple. We can skip through that. libpid you can find on kslib. The site kslib is... if someone who's familiar with it knows what that is, can you post it in the chat, the URL to kslib? I don't have it handy at the top of my head. But anyway, libpid.ks is a standard PID library function that exists in our library functions, so I'm not going to go into this in too much detail. But we all know what that is. I'll be using that a little bit, but not much. The one that matters the most is probably this one, prediction. That's where most of my work is going to be. Ah, thanks for the links. That helps. Not for this, but because of the fact that when I show the stream later, it'll be nice to have that in the video. Alright. Instead of going into all the code first, I thought it would be best if I went into the math first. So, I have... Hold on. OBS is being silly. I have to force it to reset something about the GIMP window, and I don't know why it's not resetting. Come on. I've had this problem before with OBS, and it is extremely annoying. It doesn't recognize which window I'm talking about. As anyone who's ever used the GIMP editor before knows, it pops up several toolbar windows and then the actual editing pane. And I tried telling it to put the editing pane on the screen, and it refuses to do it. This big blank black area is supposed to be the actual picture, and it isn't, and that is beginning to annoy me. I'll tell you what, I'll just remove it and re-add it. Maybe it will come out better on the second attempt. There, that's better. Alright, so one of the problems that you want to solve is how do you get the angle between two orbits? So I worked out this little diagram ahead of time. The blue-ish orbit represents me and the greenish orbit represents my target. So here's a typical example. The question is, how do you figure out where this line actually is at? Because this is not a piece of information you can directly query from KOS. Well, first job is I want to get the normal vectors to the planes of the orbit. And you can always get a normal vector to a plane by taking two lines that are in that plane, treating them as vectors, and getting a cross product of the vectors, which is exactly what I do here. I take the two objects that are doing the orbiting. Those two objects have a current position and a current velocity. And if I take the current position and the current velocity, I'm saying position relative to the center of the orbit, to the center of the planet, I should say. I guess since we're talking about ellipses, that's technically not the center, it's one of the focuses. But anyway, so if you take these two vectors and cross product them, you'll get a normal vector. Now, what this little diagram up here is saying in words is that I realized after I did all the math that because we're dealing in a left-handed system, the normal vectors really should have been drawn southward in my diagram, not northward, which is something I found out later when I went to write the code, that I had to flip a sign because of that. And the reason they should be southward is if it's left-handed and your fingers curl describing the orbit direction for this, then your thumb points down for a normal prograde orbit. Is the KSP music still loud? I turned it down. You know what? Forget it. I'm not going to turn it down. I'm going to turn it off. Even as nice as it is, because I don't know how or why it won't seem to be fixed, so... Well, let's leave the spacecraft on slightly in the it's because it's ambience. That could be. Might be just mislabeled. Okay, it didn't change anything. I clearly sent that down to 0, and it's still just as loud. What on earth? That doesn't make any sense. Oh well. Sorry about it, I don't know how to fix it. You saw the interface come up, I clearly was setting the volume to nothing, and you're still hearing it. I don't understand why. Where was I? There we go. So if you want to get that, you get the two vector, this is the position relative to the planet. Get those two, get your normal vector, there we go. Now the next thing you want to worry about is what is the burning direction. The burning direction is exactly halfway between the two normal vectors. So if you want the exact bisection of the two normal vectors, if you normalize the normal vectors into unit vectors, then just simply add them together tip to tail. The direction of that will be the direction that bisected the two. And that's what this is trying to describe here. I might be able to adjust it from OBS. Let's see if I can. Doesn't mention anything here. Doesn't mention anything there. How about if instead I just tell it to louden the microphone? That might help. If that helps or not. No, that's not a volume sensor. There's options for the sound threshold at which to mute the mic to avoid background noises, but I am not seeing anything in the settings here about just changing the general mixer between the two. Ha! Wait a minute, general mixer. There's an idea. I'll just tell Windows to do that. Maybe that'll help. There, that'll be good enough for now. So, I've just told Windows to mute all of Kerbal Space Program a little bit. That should help you out some. Alright, back to the thing. So, the diagram here, B, the adding of the two unit vectors together, is in the direction that we want to burn. But then the question is, what's the magnitude of that? You now know the direction you're going to burn, but how far do you burn? And the answer is, well, at this particular point, we're going to have a velocity that we're currently at, which I called VA, a velocity we would like to be at after the burn is over, which I'm calling VB. And if you think about this in two dimensions, merely the difference between these two vectors here is the magnitude you want for B. Now, since you want to keep the same general orbit speed, these two lengths of this triangle are the same length as each other, therefore it's an isosceles triangle. Just do some basic trigonometry, not even trig really, but anyway, just basic geometry to work out that the length of B is the length of one of the two sides, which are the same length, times the cosine of the angle between them, times 2. And then I had to throw in a negative sign because I had these backward, these vectors. So that'll get you the magnitude of the burn vector, and this gets you the direction of the burn vector. I really wish that OBS's automatic switching worked better. It's really bad at recognizing. When you configure it and say, every time I switch to this window, please switch scenes, it does it based on the string title of the window, which means if anything changes the string title, like, for example, a web browser visiting a different web page, or GIMP pulling up a different file, anything that changes the string of the title bar makes it go, oh, I guess that must not be the window you were talking about, and then all the settings don't work anymore. Really annoying. Anyway, so here we go. I don't know whether or not you saw this, but basically this is the final result down here. And there's the page up. You can check my work and see that it works. There you go. Now, the question then is, oh, you know what? Just give me a second here. Man, this is really, really annoying. I've got to find a better way to organize all of this stuff. Because of the fact that when you load a new file, GIMP won't load it into the same window, it loads it into a new window. I need to get a new capture for OBS to show. There we go. So here we are on the next page of information, which is, okay, once we've got that normal vector, then what do we do with it? Or once we've got the direction, what do we do with it? We now know the magnitude we're going to burn, we know the two normal vectors. How do we figure out the location in which to do the burn? In this diagram, the location to do the burn is point N here. How do you find out where point N is in space? Or how to get to it from where you are now? And here's what I do. Here's the two normal vectors, which we figured out from the previous page or from the cross products. If you cross product them together, you will get a vector pointing in the line of the intersection of the two planes. So this line right through here is the line from C to N. So first we're trying to figure out how do you get that CN. There it is, cross product of P to C. Wait. Oh, I'm sorry. Oh, this is not what I thought it was. Oh, this is just talking generally how to get it normal. So how do we work it out is PC1, P1C, P2C. I have to follow my own math again. I'm not quite sure what I was doing here. I just did this like over the weekend, and I'm already forgetting. Oh, okay. This is just re-deriving the normal again. P to C cross product with the velocity at that spot to get the vector. So this is just getting the normal vectors again. Is all that this is. So get the two normal vectors, cross product them together to get the CN vector. But now what you want to do is put that in terms you can actually use in your script. How do you figure that out in your script? And the answer is you can get that in terms of your true anomaly. As a reminder, if you don't remember the terms, in orbital mechanics, true anomaly means the angle from the point where you are at your periapsis to where you're talking about. So for example, this point here as drawn would be probably roughly about 85 degrees of true anomaly. The point way up here on the apoapsis would be exactly 180 degrees. So that's what true anomaly means. It's a degree measure. How far along in your orbit are you if you took an angle from your current spot to the periapsis. if we can get it in that terminology, there's more things we can do with that piece of information. So how do you work it out? If the ship is currently here, and you know the ship's current true anomaly, which is a queryable thing, then that means you know the angle from PE to ship's current position. You know this angle, because the ship actually already tells you that all the time. You can directly query that from. If you add on to that the angle from here to here, you'll get the angle of the whole thing. And that is basically what this is doing right here. The vessel's current true anomaly plus the angle ahead. The angle ahead is the angle between this vector and this vector, as such. Now there is a little bit of extra work not shown here because of the fact that this angle will never give you a number higher than 180. So if n is actually all the way around here behind you, you have to do a little bit more fiddling to get that to work. But I can get to that when I get to the code. This is the basic idea of finding where in true anomaly is this. Once you know where it is in true anomaly, then you're set, because from that measure you can get information about time and so on. So now let's go to the code. This is the math to simply figure out, given a current, or given any particular true anomaly. I need to switch my window, don't I? There we go. Given any particular true anomaly, find the ETA to get there. So here's the object you're trying to predict its orbit for. What degrees of true anomaly are you talking about? And this just runs through and does it by calling some other functions that do the work. The other functions that do the work are down here. Time PE to TA is how long does it take to get from periapsis to a particular true anomaly on a particular orbit. So all I'm doing up here is taking that result and figuring it out relative to where my ship currently is. So you look at where the ship currently is in its time since periapsis. You look at where the thing is you're talking about in terms of time since periapsis, and then work out the difference between the two to get how many seconds into the future it is. And then this is some work to work out that if it's actually behind you, you have to add an entire orbit period to that, because you got to go around once to get to it. Wow, that's wrong. I just realized this is completely wrong. It's amazing the things you notice when you show something to someone else. If it's negative, what I really... yeah, it shouldn't be more than one period. It should be... oh, no, this is right. Because of the fact that it's negative, that means this is really a subtraction. Right here. This is actually orbit period minus TA. So no, actually that was correct after all. I spoke too soon. Alright, so how do I figure out the time from periapsis to a particular true anomaly point? This is standard stuff you can find on Wikipedia if you actually Google this question. This is nothing me. This is me not doing anything particularly fancy. Well, okay, a little something fancy, but not too bad. I have that on another page over here. Let me pull that up as well. Oh no, I don't. Never mind. I don't have that diagrammed out. But this you can find online fairly easily. And I'm not going to go into this in detail right now. But what this gives you is... let's see. Given the degrees and given the time from the periapsis to there, by first working out the eccentricity and the semi-major axis, which the mod just tells you directly, and from there you can get what the anomaly is in degrees, the same thing in radians, and then by the way, this is one of the things that does annoy me about working with KOS. The decision to use degrees instead of radians was made long before any of us got our hands on it. And there are certain math formulas in which doing things in degrees does not work nearly as well as doing it in radians does, and this is one of them. So we have to have this weird mixture of sometimes measuring in radians and sometimes measuring in degrees, because the sine function as built by KOS expects degrees. So this is one of the places where it really needs to work in radians, but we can't use radians here because sine expects degrees the way we've implemented it. But you can do this math, and it does work. This is the thing I was describing earlier, getting the normal for any particular orbit with that cross product. That's nothing special. This is finding the ascending node where orbit 1 crosses orbit 2, and it's returned in terms of a true anomaly of orbit 1, how far into orbit 1. This is doing the exact math I just showed on paper. So there's the two normals. Cross product the normals to get the vector to where the node is. Get the position of get position of the ship that is in orbit 1 currently, like this. How many degrees ahead is this point from this point, which is a angle between the two vectors. Sign check is to see whether or not this needs to be flipped because it's more than 180. If it needs to be flipped because it's more than 180, then subtract it from 360 to get the other side of the circle, and then return that, if necessary, modded with 360 as just a safety check. I don't actually think I needed to do that, but just in case, it's been done. And there you go. Now this implements that whole page of stuff I showed before. I'm not going to show inclination match burn yet. Orbit altitude at TA I'm not going to show yet. Actually, yes I am. This matters. I've got a question over here. Have you considered a rad to deg function so you could use sine of rad to... I thought about it. It's not that big of a deal one way or the other. I could easily encapsulate that into a utility function. As far as radians and degrees go, it works as long as you keep straight in your head the fact that all the trig functions that KOS provides require degrees, even though oftentimes when you go look up formulas online from science texts, they're written in radians. And yeah, it's usually important to go check that science text you're getting the data from, and just read it with a fine-toothed comb. Scan it with your eyeballs for the word radian. Because typically if they're good, they will warn you, by the way, the math we've done here only works on radians. But the tricky part is, when you convert everything into radians and you think in a radians world, the tricky part is remembering in your head to convert it back to degrees again in order to send it to our trig functions. I'm not sure what a good solution to make that easier would be. We could easily switch all our trig functions to radians, but then we would have a massive backward compatibility problem. It may be that we could make it a setting. You could perhaps set a setting somewhere globally that says from now on all the trig functions are radians until you change the setting. That might make it a little easier. I'm not entirely sure what the best way to do that is. At the moment, I'm just doing it by manually converting every time. Okay, so once you've worked out where the ascending node is in terms of true anomaly, you can then work out how far into the future it is with this function. When you... yeah, lazy degrees, that might not be a bad idea. Actually, I take that back, that would be a bad idea, because compiler directives have to be at the top, and this would be something you'd want to be able to switch back and forth between modes throughout the duration, so it'd have to be something that gets executed on the fly, not something the compiler does up top. Okay, where was I? So when trying to work out what the inclination matching burn should be, a burn consists of a time in the future when the burn will happen, and a vector that represents the delta V of the burn. And this should look familiar to anyone who's worked with maneuver nodes. This is basically what a maneuver node is. It's a delta V vector at a particular time. Only I'm imagining that we're doing this when we don't really have real maneuver nodes to work with yet. So instead, I'm returning a list of 2 items as a sort of poor man's struct. The first item is the universe time, not ETA time, of when the burn is, and the second one is what is the actual delta V vector. So you pass in a vessel that's going to be doing the burn and an orbit that it's trying to match up with. Notice this isn't an orbit like all the other ones are. This actually has to be a vessel. You can't pass in a body, and it has to do with one of the function calls in here that I make. It requires it to be a vessel. That's a little bit more limiting than I'd like, but at the other hand, you can't move the moon anyway. So if you're talking about an inclination burn, you assume the burn is being done by a vessel anyway. Yeah, good point about trying to detect if you have a radiance problem. When you start seeing weird random results and changing angles, you're totally right. And that's actually, HVAC is talking about something that he actually helped me debug in this very script over the weekend when I was working it out and showed him some of the problems I was having. He actually detected, hey, you've got a radian degree problem right there. And that actually helped a lot. So he knows what he's talking about when he says this, because he actually helped me debug this problem. So first thing I do is, what is the ascending node at TA? I covered that function. Find the intersect, get the true anomaly relative to the vessel 1's orbit. Then I'm either going to use that ascending node, or I'm going to use the descending node on the other side. The one I want to use is whichever of the two happens to be at the higher altitude, because that's the one where the inclination burn will take less dV to do. And the way I work that out is simply, am I closer to my own apoapsis or periapsis? And I don't need to do any extra work to figure that out. I already know that, because true anomaly is how many degrees are you from your apoapsis. Or, I'm sorry, how many degrees are you from your periapsis? So basically, if I'm in the sector of the degree arc that's closer to PE, then the angle will tell me that. So if the node that it found is less than 90 degrees, or between 270 and 365, if it's in that section, then you're in the half of your orbit that's closer to periapsis. If it's in the other section, you're in the half of the orbit that's closer to apoapsis. And if the ascending node is in the periapsis half, then flip it by 180 degrees to get the one that's in the apoapsis half, basically. So I don't care whether I'm doing this at ascending or descending node. Either way is fine. I just need to know which one's higher. Alright, once I've got that, node TA is the true anomaly of the spot where it will happen. I need to work out when it will happen. The ETA is the ETA that I have to get to that node, so now I know how many seconds into the future the burn will occur. I want to convert that into universal time. That's what UT is. I want to convert that into universal time, so just add it to the current time. That's simple enough. I want to work out what the unit vector is. This is the unit vector in the direction to burn, which as I described in the math before, is simply add the two normal vectors together tip to tail, and then normalize that to get the unit vector in the direction of the burn you want. And then the velocity that I will want, or the velocity that I anticipate I will have when I get there, before I do my burn, is done with this function called velocity at. If you look up on the KOS documentation, this is a function we provide for you. You give it a vessel, or actually any orbitable object, it could be like a moon too, and a universal timestamp, and it will tell you the velocity pair at that spot. Velocity pair as in both surface and orbital, and you have to use the colon orbit or colon surface suffix just like you would with, say, ship velocity orbit. It's the same kind of thing. And the reason we provide this to you with KOS is because mathematically this is a thing that's impossible to solve without a numerical method that has to run a bit of a series to work it out. And trying to work that out in KOS code is going to mean you're going to be running a loop that's kind of slow. If we do this under the hood in the C# code, we can run that loop like that and be done with it. And in fact, this is actually what happens inside of Kerbal Space Program itself. When you have the tracking center upgraded to the point where you can see your predictions. Those predictions are coming from doing numerical approximations, which incidentally is why they wander and waver so much. You know, you're looking at the thing that says, oh, I predict when you get to the moon you'll have a periapsis of 10,000 meters. Then you're looking at it and it's like, no wait, I mean 11,000. No wait, I mean 9,000. No wait, I mean 10,500. And it just keeps wobbling back and forth. And the reason is because it keeps rerunning the approximation multiple times a second, and depending on how far it gets into the series before it says, okay, I've been taking too long, I'm going to cut it off, you get a different level of precision. And they can't make it too precise because it would take a long time and slow the game down. So we kind of have the same problem here. I forgot what my epsilon is, but I think I decided that as long as it gets within, I think it's like 0.01 degrees or something like that, it considers it good enough to return it back to you. I'd have to go look at the C# code again to remember exactly how precise we let this get. But anyway, there it is. It's built in for you. You can use. Predict your velocity at any future time. So I do that, get the velocity vector at that point. Now that I know that, I can work out the burning magnitude by the formula I showed you on the previous page, which is just written out here. So now I have the magnitude of the burn, the unit vector of the burn. If I scalar multiply the magnitude by the unit vector, I'll get the vector of the burn. So then I return a list consisting of the time and the vector of the burn. This is doing the meat of the work. If we show what actually uses this, which is the program called Match Inc. This is the entire program, Match Inc. That's the whole thing. It's very small. I can fit the whole thing on the screen right now. It runs prediction, which is this list of libraries I was showing you before, and a thing called burn util, which is just a very tiny thing I'll cover in just a second. Won't take very long. And you run it telling it what the thing is you want to match with. It runs inclination match burn, the thing I just showed you, which gives you the two pieces, the universal time and the delta V. It works out how long it expects that burn to take. Burn seconds is part of burn util I haven't shown yet. How much time ahead of time you should start your burn, which is basically take that delta V, cut it in half, and try to time it so that half of your delta V occurs before the moment in time of your burn, so that the other half occurs after the moment in time, which isn't exactly halfway, because as your mass goes down over time as you burn fuel, you will do more delta V toward the end of your burn per second than you were doing toward the beginning, and that's what this burn seconds is trying to do, is to work that math out for you, so you can time exactly when to begin your burn. Once I've done that, this is just some nice graphical prettiness to show you on the screen a vector that will have its tail sitting at the ascending or descending node where the burn will happen, and it will be pointing in the direction of the burn to show you this is where it's going to happen, just to give you a visual aid on screen. And then in a loop, it's just going to play with that, basically. It does keep moving the tail of the vector because everything is done in coordinates at which the origin is your ship. If I didn't keep moving the tail of the vector, then as the ship moved, the vector on screen would move with it and go off of the point I put it at. So the purpose of this loop here is to ensure that as I orbit, I keep resetting the tail of where the vector is, so it stays on the right spot, recalculating it again and again. And then finally, it does the burn. Oh, hey, you know what? This is why my vector wasn't disappearing off the screen. I forgot that part earlier. There. So after the burn is done, it sets this to true, which causes this when loop to stop. Or not really a loop, but you know what I mean. It prevents the when trigger from continuing. So in the background, it'll keep doing this until I get to this line of code, and then it'll make the vector stop and go away. Do burn with display is also a part of burn vector, or burn util. Burn util right now just consists of two things: burn seconds prediction and do burn with display. Burn seconds prediction is a standard thing. People have made this before. It's actually in the KSLib library. But if you're curious to know how it actually worked, I can show you in just a second here. Okay, this is basically solving the math problem. If you are trying to get to a given delta V magnitude, and you know the ISP of the engine you're going to be burning with, and you know the max thrust because you assume you're going to be burning at throttle 1 the whole time, and you know the mass you start at before you begin the burn, you can work out from this information how long a burn will take to get to a given delta magnitude or delta V magnitude, making the assumption that you're not staging in the middle of it and starting a new set of engines with a new ISP and a new kind of mass. I did not do the work here to deal with that scenario. That's a much more complicated scenario. It can be dealt with, but for my example, I left that complication out. So this assumes you get to do the entire burn on the same stage you are currently using. So you start from the standard rocket equation, which you can find online if you actually just Google the phrase rocket equation. It's a well-known thing, which says that given how ISP is typically measured, if you want to know how much delta V you're going to get for burning a certain amount of fuel, and you know the ISP of the things that are doing the burning, then gravity at G0 is gravity at sea level of your standard unit of measure for weight, i.e., you know, if you're using imperial systems, what gravity are you measuring the ratio between mass and, like, pounds? ISP is one of the strange things where the imperial system has left its imprint on even the metric world, because it was originally designed to be a measure in which thrust, which is actually a force, and weight, which is actually a force, get chunked into the equation together in a way that cancels units out very conveniently. But it doesn't quite work so well in metric, because in metric you don't measure how much stuff you have by its weight, you measure it by its mass. So when you're dealing with this in metric, it's one of the weird cases where metric is actually slightly more complicated than imperial. Usually in every other case it's the other way around. You have to multiply the ISP by gravity at sea level to get that conversion in there. So anyway, multiply by gravity at sea level, take that times the natural log of these two masses. The two masses are the mass before the burn and the mass after. So this is the ratio of how much mass you ate up during the burn. And this is a standard equation. I'm not going to go into how that's derived because that's getting a little bit beyond me at this point. But once you've got that, you can work out through just basic simple algebra stuff how to solve for M1. So what we're doing here is first trying to figure out just how much fuel do you deplete to get that much dV. Not taking into account how long it takes, just how much fuel did you actually use up in mass terms. So you run through the algebra and get this term over here, delta V divided by gravity 0 ISP is natural log of M0 over M1. Well, once you get this, then to solve it you have to take e to this, as shown here, to get that. Notice that this ratio is exactly the... No, this part here is very, very weird to me. It took me a while to realize what they're doing here. The change in mass is the mass you began with minus the mass you have at the end. That's simple enough to understand. But this step here does something you don't normally see in algebra problems. This makes the equation more complex rather than simplifying it. It's taking this and doing the opposite of simplification, but for a good reason. M0 minus M1 is the same thing as M0 times, in parentheses, 1 minus M1 over M0. If you work this backward and simplify this, you'll find out it's actually the same thing as this. Now, why would you make it more complicated? The reason is to get this ratio to look a lot like that ratio, but swapped. Notice those look the same, but swapped. Why does that matter? Because, given this over here, we know that e to all of this is the ratio m0 over m1. Therefore, if you flip it, you get 1 over all of this, which is what this term here is. This is m1. I'm sorry. Yeah, this is m0 from this equation here. Why does that matter? Because this transformed this into givens. This may look like a mess, but it is all made up of givens, so that you can calculate it out in your code. And this simplifies slightly because when you're dealing with exponents, 1 over something to an exponent is the same thing as that thing to the negative exponent. So that's how this flips to this. This is your final answer, how much mass you took. Okay, so why do we care how much mass we lost in the burn? The reason we care how much mass we lost in the burn is because if we know the ISP and we know how much mass was lost, we actually know how long it takes to lose that much mass. We know how long it takes to burn off that much fuel, because that's kind of what the definition of ISP is, really. At a given particular thrust setting, how fast are you getting rid of your fuel? And if you just work out from the basic definition of what ISP means, you get the change in mass per second is equal to the force over the GeoISP term. Run through this, sticking delta M for all this mess up on top of the numerator. Because, of course, sticking this down here because you're solving for t in this case. If you're solving for how many seconds it took to do all of this. Run through the algebra, you get this ugly, ugly mess. When you run this long formula, you will get how many seconds it takes to get through this much mass, which is how much mass it took to cause this much dV. This may look like a mess, but you can hide it inside of a function, and everything you see in here is a given. So now that you know how long the entire DV burn takes, to figure out when you want to start the DV burn so that it straddles the time point you wanted, all you have to do is plug in half the DV you wanted here instead of the full DV you wanted. Plug in half the DV you wanted to find out how long it takes to burn half of it. And that's how much earlier than the point of the burn you want to start. So that's how that math works. This has been done before. People have made this, they call it usually exenode, execute a node, only I've done it in a way that avoids maneuver nodes. So burn seconds is running through this exact formula I just gave. So this, what you see here, is the formula from the previous page. This is looping through the engines to figure out just the ISP of some particular engine. This is a very crude thing that assumes all your engines are uniform, and that's mentioned up here in the comment. I'm assuming that even if you have more than one engine, all of your engines are going to be the same as each other. And this is crude. There are people who've made this better, but this just gives you the idea, gets it across very quickly. And that calculates burn seconds for a certain delta V magnitude. To actually do a burn, then, is quite simple. Aim at the direction of the vector using simple lock steering. That's all I'm doing here. I'm not doing cooked steering for this. And then burn for the number of seconds predicted by burn seconds. And if you look through this code, that's really all it's doing, with a slightly incorrect thing at the end. In which it slows down a little bit right at the tail end of it, which isn't quite right. But I was finding that when I burned at the full speed, it tended to not cut it off quite quickly enough, and I figured I'd rather be slightly off on the time than have it burn for an instant longer than it should. And that's why it, where in here does it do that? I might be talking out of my butt here. No, this does not do it. This goes full throttle all the way to the end. I'm sorry, I'm wrong. I was thinking of a different thing I did where I cut the throttle down to like, oh no, here it is, right there. So I do bring the throttle down when I have less than 10 delta V left. I cut the throttle back down to a slightly smaller amount for just that last moment. The dV to go is calculated vector-wise rather than time-wise. I was a little bit wrong. I'm not actually using burn seconds in here. I'm actually calculating it out by going, here's the velocity I started at, and if you work this thing here out, what I'm actually doing is saying, I want to know how much my velocity has changed in the direction that I am pointed, or in the direction that my dv is pointed. So if you take a dot product of the dv vector and the relative difference between where I started, the velocity I started from and the velocity I currently have, and then take the absolute value of that, because sometimes the dot product will get you a negative number if you're going backward, and then square root that, I'm basically getting back to the magnitude of how much I've burned. But in a way that remembers the direction. The reason that takes into account the fact that maybe I was trying to burn this way, but for whatever reason my steering was wobbly or off and I actually burned that way. It means your delta V never actually hits 0. I'm sure you've seen this playing it manually. You put a maneuver node out there, you burn at the maneuver node, and you watch the maneuver node's delta V remaining bar go down to 0 as you burn, but you watch it, it never quite hits 0, and then starts going back up again. And the reason is because your aim wasn't precisely spot on. If you were just a little bit off, then if this is the spot you were aiming for and you were skewed from it, the delta V is a magnitude of a vector. So if I've burned this much, but I'm not directly at the point I was aiming and I was instead over here, I still have that much difference that's being registered. So what I'm doing here is nulling that out by only paying attention to the component of my change that is in the line of the burn and ignoring any component to the side. Thus the use of the dot product to do all that. So now that I've put all of that into place, I can show you the magnitude correction. I've talked about the code and the math for a little too long. Let's actually go see it. And I need to remember to flip this. There we go. Now, because I'm just testing out the script here, I'm cheating a little bit and not using remote tech, and I'm allowing myself access to the archive from a distance. Again, that's because I'm testing the code rather than actually using it in a real game. In a real game, I would consider this cheating. I'm going to reverse video because I think that might show up a little bit better in the feed. Oh, right, I forgot a step. When I do my editing, I do it in my own directory that's not part of the game. So I have a routine here that I run, a little Perl script I made, called export.pl. Oh, right. That when I run that, it does nothing more than take all the chaos files it finds in here, run them through a stripper that takes the comments out and the indentation out, because this dates back to when we had very little space on the drives, and then copies all that over into the archive that's actually used in the game. So every time I make an edit here, I have to go over there and do that. Okay. Now we have all the stuff. I want to run match inc, passing in, what was the name of it again? The thing I'm trying to match to is called Tilsa Adrift. Okay. Okay. I'm not sure what you mean by a minification script. Okay, so it calculated the burn vector, and it showed it on screen. If you zoom in here... Ah, you're right, I didn't flip you back. There we go. Let me do this again. You don't like the clicker? Oh, I like the clicker. Okay, fine, I'll turn it off. So I ran it, giving it the name of the vessel I'm interested in. It finished its calculations and decided that this is where it thinks it needs to do the burn. You can see the little vector on screen. It thinks it needs to burn this way at that point. And if you look at it, that does look about right. If you try and aim the camera to line this thing up, you can see that seems about right. In fact, why am I doing this with this? Why not just turn the tracker on so you can see? If you look, it picked the spot that the tracker says is the node. Alright, so let's see it in action. Now my script does not automatically warp. A lot of people have their scripts automatically warp. I generally avoid that because I consider warping to be a feature of the boredom of the player, and it's sort of breaking the fourth wall. About the only thing that I do automatically is check to see if I am warping, and sometimes I knock the warp down to 0 when I'm getting near the point, rather than to actually make it start warping. So I let the user warp if they feel like, but then knock them out of warp as I get close. Now it is burning. You can't hear it because I turned the game's sound off, but if I show you on screen, you can see it is burning. The burn DV remaining is getting down near 0. And it slowed down as it got close. And is done. Oh my, that didn't happen before. Uh-oh. And as you see, it wasn't perfect. The ascending node is still 0.3, but it got close to the right orbit. I can probably work on making that a bit better. Chances are what would make it better is to up my IPU and make it burn exactly at throttle 1 until the cutoff, and just cut it completely off without that 0.1 factor at the end. But I didn't do that. Yeah, I should go find a... You're right, I should go find a Kostev. I wonder where I'd find one. That is not pleasant to see that. I'll have to look up later what that was. Okay, so there we go. That's the match inclination part. Is there anyone who is confused by anything that happened so far? I'll ask that question out loud before I move on. Anyone? Going once? Going twice? Oh, that's right. There's a delay in the chat. I have to wait. Okay. Alright. I shall move on then. So what's the next thing you want to do? Well, the next thing you want to do is... my orbit is still entirely contained inside the other orbit. So one of the first things you're going to want to do is enlarge the orbit till it crosses at some point. So how do I do that? Well, my next program I run after this is called Rendezvous. Really? Hang on a second. Yep, that's why I had another VIM window open with the same file. There we go. Which you can't see on screen. Oh, I forgot to flip the mode, didn't I? There we go. Okay. So Rendezvous is the one that actually does the rest of the burn. Yeah, I see what you're saying about the Periapsis problem happening. I'm not exactly sure why that happens, but it does. I've noticed that happen a lot myself, and I don't really get why it does. It's getting down into the innards of KSP itself, rather than anything we've done. Hold on a second. There, that's better. I get that thing too, where sometimes if I rotate the craft, the act of rotating it actually moves the apoapsis and periapsis. And I go, what? I don't quite get why rotating in place behaves like it's ever so slightly thrusting you. But that's a base game issue, that's not my issue. So, how do we figure out whether or not we are intersected? Well, I have a routine in prediction called orbit cross TA. Let's go into that first. Anything I end in TA, I usually mean true anomaly, by the way, just so that you know. Oh, hang on a second. There, that's better, sorry. Sorry about my voice. I'm starting to lose it a little bit. Okay, so I'm trying to figure out, given two orbits, at what point do they actually cross over each other? And I could not find an easy, good way to do this analytically. There probably is one, but I didn't work out what it was. So instead, what I came up with was a crude, iterative algorithm to find it. Rotating the vessel moves the comm relative to the root part. Oh, yeah, I can see that. I can see it causing wobble, but what's weird is that I've had it where I keep rotating the same way, and instead of the periapsis going up, then down, then up, then down, then up, then down, it went up a bit and down, and then up a bit more and down, and up a bit more and down, so it was actually causing it to move up more and more and more, rather than just waggling back and forth across the same point. That's really weird to me. Anyway, orbit cross TA, orbit 1, orbit 2, max epsilon, min epsilon. This is fuzzy tweaking. Basically, because it's doing an iterative search, rotate to Joule. Yeah, because this is doing an iterative search, there's always that trade-off between, would you rather have it be accurate, or would you rather have it finish quickly? And those are in direct contradiction to each other, so I decided to leave it up to the person who calls the function to say where they want their tolerances. So it starts off with a certain number of degrees to start the search at, and then how many degrees to tighten it to the point where it decides it's done. The basic algorithm is, you can get predictions for what the altitude at a particular point in an object's orbit is. So if you can figure out what the altitude at a spot is, all you have to do is take the two orbits and figure out how they're aligned with each other, how their true anomalies relative to each other are arranged, so you can put one orbit relative to the true anomaly of the other orbit. And then going around the ring, once 360 degrees around it, look at the two altitudes of the orbits and watch when the two altitudes flip, and one becomes bigger when it used to be smaller. So the way that I'm doing that is I'm moving by large degree increments at first, like let's say for example 10 degree increments, to find the first spot where it flips which one was bigger. That means that that was a crossing point somewhere in that area. And then once I figure out that that happened, I then go into going, okay, let's try a smaller epsilon and a smaller one and a smaller one, until it narrows down where it was. The danger with this kind of algorithm is if I set the initial epsilon too large, there's a possibility that you could get, let's say this is one orbit here, and another orbit goes up and over it just a little and comes back down like this. If my first epsilon is large enough that I'm taking a sample point here, I'm not sure if I'm getting this in camera, a sample point here, and another sample point way over here, and the cross happened entirely between the two, it won't catch it. So that's the danger of setting that too large. The danger of setting it too low is that it scans really slowly till it finds that first hit. So it's a fuzzy guess. So first I have to figure out how far off one orbit is from the other's true anomaly. Basically, I want the angle between their periapses is. Periapsises? I don't know what the plural would be pronounced as. But wherever that point is. And that's TA offset, which is here, and that is extremely quick and simple. I can figure out a orbit's periapsis's longitude in the solar system's longitude system, not the body it's orbiting around, but the longitude of the entire solar system, which has a zero longitude, although the game never shows it to you. It does actually have one. By working out the argument of periapsis, which that's one of those terms that you have to go look up to see what it means. That is, and the longitude of ascending node. The argument of periapsis is basically where your periapsis is relative to the universe around you that the solar system sits in. Periapses, yeah, I guess periapses would be right. Anyway, so you work out effectively where orbit 1's periapsis is by going, where is its ascending node, the spot where it crosses the equator, that is. It's not the spot where it crosses the equator, that's the ascending node relative to the universe. It's ugly, but this works. This tells you... this does tell you, in fact, where your periapsis longitude is relative to some unknown arbitrary solar system longitude that you don't know what it is and don't need to care what it is, actually, because we're going to transform this into relative terms. Orbit 2's periapsis is this. You care about the difference between them, so now it doesn't really matter what the original universe's longitude lines are or how they're oriented, because you're converting it relative to something that's relative to each other. You don't care what the original format was at that point. So you work out the true anomaly offset between the two orbits. Stick that here. Start off with an increment equal to the starting epsilon we began with. Everyone's talking about how to say multiple periapses. Periapsides? Oh, so is it kind of like octopodes? Anyway, instead of saying octopuses. I always thought octopodes sounded like you're talking about an animal that has a multiple of 8 legs. Like, a single octopode is a set of 8, so an animal that had 2 octopodes would be a 6-legged animal, or a 16-legged animal, and you know, if it had 4 octopodes, it would be like a 32-legged animal. I always thought that's what octopode sounded like to me. But anyway, an octopi has 8 times 3.14159 legs. Anyway, this loop that I've been getting distracted about octopuses, this loop is trying to work out the algorithm I just described. So it starts from the orbit's current position, its current true anomaly, sticks that into a starting variable. Then in a loop, until it finally has done a full 360 around the orbit once, or it hits a spot where the increment that it has gotten to is smaller than the minimum epsilon, which means you found a hit. Keep doing this. What do? Find out the diff between the two altitudes. So what is it? It's the altitude at the current true anomaly, and then the altitude of the other orbit at its measurement of the current spot. Whatever the difference is between those two altitudes, figure out whether or not it's the opposite of the way the difference was the last time you went through the loop. And I'm just figuring out whether the sign changed. So I multiply them by each other, and if I multiply them by each other and get a number less than 0, it means these two must have opposite signs of each other. Either diff is negative and prev diff is positive, or diff is positive and prev diff is negative, but they have to be opposite signs for this to come out negative. If they're both negative, this comes out positive. If they're both positive, this comes out positive. This is just a very quick trick that a lot of programmers have used in the past. It's a very commonly known programming trick. to quickly check whether or not a sign changed, is to just do this. If you don't care about whether it's changed positive to negative or negative to positive, if you consider either one just as good. If I find a change, then I inverse the direction of the increment and make it smaller. So increment is now going to go the opposite way to the direction it went before because I just passed a hit. And I'm going to make it go smaller. So I continue the loop now going in the opposite direction until I find the hit again, and then I reverse the direction and go smaller until I find the hit again, and then I reverse the direction and go smaller until finally the size of the increment is small enough that we've hit the spot. Yeah, that positive-negative trick, I hadn't occurred to it either. I read it in someone else's code about 10 years ago, I think, and I thought, well, that's brilliant. Why don't they teach that? And then I found out that they did, just not at my school. Anyway, that's a very common trick that lots of people use to just watch for the change in a sign. When you get to the end, return the true anomaly that you got with some work to flip it, depending on whether or not it's... Oh, actually, no. This is -1 as a signal saying, I didn't find anything. Which is, if you ran this right now, on the current situation, where the orbit is one orbit is entirely inside the other, then in that situation, this would return a -1. So, -1 is just a special flag that says I didn't actually find a hit, there isn't one. Otherwise, return the value. Again, for safety's sake, mod it with 360 in case something in the algorithm accidentally made it go bigger or smaller. Actually, not smaller, that still wouldn't fix it, but it will fix it if you accidentally got it to be bigger somehow. I kind of do this as a boilerplate these days. I don't even think about whether it's possible for that condition to occur. Okay, so that's how I figured this out. I didn't cover what orbit altitude at TA is. That's actually this. It's a very small, simple formula, which I don't have a diagram for. But again, you can look this up. It is a well-known thing. You can just Google for, how do I find the altitude at a true anomaly of an orbit, and you'll see this exact thing right here. It is a well-known thing, so I'm not going to go into it. I'm just going to tell you, if you look it up, you'll see it online in any kind of orbital mechanics textbook. But it's in terms of radius. And the only thing to remember is, of course, radius is from the center of the body, and I wanted to return it as altitude, so I have to subtract the body radius off of it to get the altitude. Okay, so that finds the spot at which a cross happened. Again, why does that matter? Because the first thing the script is going to do is find the next existing intercept, and find it again in terms of true anomaly. So that runs this, my ship's orbit, the other thing's orbit, start off at 10 degrees initially. If you find a hit within 10 degrees, keep narrowing it down till you get to less than 0.01 degrees. If after trying to run that, you get a negative result, remember I used -1 as the flag to say no hit was found. If you return a -1, no hit was found, so before we begin the rest of the work, we have to actually cause a hit to exist. So it prints on the screen that there's no intersect point. How will it make an intersect point? It'll either have to burn a bigger orbit or a smaller orbit to cause an intersection. Now, it needs to know at this point whether it's the inner orbit or the bigger orbit. So to work that out, I just realized I keep pointing at things in the game that you can't see. So to work out whether or not it's the bigger orbit or the smaller orbit, raining where you are? No, it's not raining at all here. Yesterday it was horrible, but today it's fine. Alright. No one wants to hear a Twitch stream where someone talks about the weather. What am I doing? This part here is what I described earlier, where I never make my scripts do warping, but I might make them drop out of warp. So if I happen to choose to warp to get to Periapsis, it'll notice when I'm getting close and start dropping me out. How soon it drops me out depends on how fast I'm warping. The faster you're warping, the more prelude time it needs to drop you out to avoid going past the spot. No, don't apologize. I'm mad at myself for talking about the weather. So this just drops you out of warp just before Periapsis, in case you saw this message on the screen and decided you'd like to just hurry up and get to Periapsis. May have to enlarge or shrink. How does it know which it is? Well, we already know the orbits don't intersect, or we wouldn't be in this section. So if the orbits don't intersect, you can just look at their two radii. You can just look at the two diameters and go whichever one is smaller is the inner one. If they don't touch each other, that has to be the case. So I just basically look at the diameter of the two orbits. Now, of course, we're talking about ellipses, so the word diameter is not quite right. So you use the word semi-major axis to basically mean the long diameter, so to speak, of the ellipse. So whichever of the two is smaller, that tells you whether I'm the bigger orbit or I'm the smaller orbit. Depending on which it is, it either points prograde or retrograde before it starts the burn. Wait until it hits Periapsis. I could have used ETA Periapsis for this. I don't know why I chose to use True Anomaly, but this works fine. Your True Anomaly is 0 when you're at Periapsis, and presumably if you time warped until you hit this point, that would mean that where was I? That would mean that you'll be at the high degrees of True Anomaly, be like, 350 or 355, a few degrees behind 0. When you finally cross over the 0 point and are not in the 355s or whatever, you hit this quadrant and it goes, okay, found it, now we can burn. Blocks the throttle to 1. And now, with the throttle being 1, it's burning either prograde or retrograde, depending if it makes it bigger or smaller. Now, how does it know when to stop? It will stop when it found a hit, which means I have to rerun this as I'm burning. So this says, until we find a hit, keep looking for a hit. Now, yeah, I've looked at LAS, look at it a little bit more. It looks handy, but I haven't looked at everything in LASCalc. Space is hard. In here, I'm running it in cruder mode. Notice this time I said I want an epsilon of 1/100th of a degree. Here I'm saying 2 degrees, much cruder, because this test is going to be happening over and over and over and over and over again, and therefore I decided I wanted it to be a quicker test, so I pass it in a larger epsilon. I don't need precision here. I just need to find the spot where you start getting it to cross a bit. Once it finds a spot where it starts getting it to cross a bit, it shuts down the engine, and now that it's stopped, it'll get the measurement one more time to make the preciser measurement. So this time I'm back to hundredths again. So now I have the intersect True Anomaly down much more precise. And I know that that is the point of the intersect. Or, if I already had an intersect, then none of this ever got executed, and the intersect TA that it had from up here at the top was already fine. Alright, so now what do I do after that point? I need to know the ETA to the intersect. I know the true anomaly of it, but I need the ETA to it. Well, as described before, I already have a routine to get the ETA to any particular true anomaly, so I use that. Next, I want to find out when that is in universal time rather than current time. So take the current seconds, add the ETA, and now I get the universal time version of when the intersect is. Now, the offset I am from my target ship, I figured that out, which again, this is already stuff I've done before. Now I want to know what is the true anomaly of the other ship's point of view of this intersect that we share with each other. This is a point at which I will get to this point on my orbit at some point in time, and my target is going to get to the same point at some point in time. But when the target gets there, its true anomaly won't be the same as mine because our two periapses aren't in the same spot. We could be like this from each other. So what might look like a true anomaly of 30 degrees to me might look like a true anomaly of 45 to my target. So this is getting what my true anomaly is, or what the target's version of the true anomaly of this commonly shared spot is. So using the offset that I am from the other one, add on my true anomaly to that offset to get the true anomaly in its terms, and then figure out its ETA to that spot. Why does this matter? Here's why it matters. I'm going to go get a list of what are the next 5 universal times that the target will get to this spot. So using this ETA and the current time and this little loop, I go to get from 0 to 4 a list of the next 5 times that it's going to come to the same spot. Yeah, I've heard good things about Orbiter, but dang it, I want to build my own ships. The thing about Orbiter is, what I've seen of it is you're flying pre-made things, and I want to make things, and that's why I haven't really gotten into Orbiter. Even though everything I've heard about it says that its science is even better than KSP's science. And that would normally appeal to me were it not for the fact that I want my Lego stuck-together rockets. I like the Lego stuck-together rockets. Okay, so I've got the list of when the next 5 possible intercept points could be. Now I've got to figure out, when are we going to hit the intersect point? So, intersect first U time was this already figured out up here. This is nothing more than a stupid wait till I get there that continues to print the wait time on the screen. So I can skip over that, everyone knows how to do that. As I get within 20 seconds of it, I start locking my steering early. And the reason I'm doing this early is because of a common problem with cooked steering in KOS, which, dang it, when are we going to get around to fixing that? Where it wobbles all over the place, and I want to give it a good time ahead of time to get it nailed in. And it takes a long time on this particular ship design to get it nailed in. It wobbles all over before it finally settles in. And it only settles in when I have the SAS on. I need the help of the SAS to dampen it, or it would just spin all over the place. And again, this is just really making me embarrassed by the fact that our cooked controls really need to be given a proper PID controller. It's been ages. We keep saying we're going to fix it. I keep not touching it because I want someone else to look at that code instead of me because it's not my code. But dang it, I'm really getting sick of the fact that our steering looks so embarrassingly bad. We really got to get a handle on that. Okay, once I've gotten to there, I will embiggen my orbit until one of the times matches. I always embiggen, I never smallin, and the reason is because I don't actually know the this avoids the problem of trying to make sure I don't shrink my orbit so small that I start dipping into atmosphere, or even worse yet, dipping into ground. I just avoid the problem by saying I can always try to find a rendezvous by making a bigger orbit. Then I know I'm not going to hit the ground. Space is hard. Yeah, I know that there's a mod that lets people adjust the PIDs that are built into KSP, but what this person's talking about is a mod to tell is to have KOS be told the PID parameters to use, rather than telling KSP's SAS system what its parameters should be. We'd be telling KOS what the parameters should be, and I think that's a really good idea. The first step is to make KOS's cooked steering actually use a PID controller, which to the best of my knowledge it kinda isn't at the moment. That's one of the reasons it's kinda flaky. Anyway, so, in beginning the orbit, here's my algorithm for that. This, by the way, is the part that is really bad. I have found that when I try running this, I end up with like rendezvous that are, well, you got within about 10 kilometers, and it's really, really inaccurate, and I'm not quite sure why. Is it because all this conversion to time invokes lots and lots of floating point errors that compound? Is it because I've got an error in my math and it's not just floating point error, I'm actually doing something wrong? That's the part I'm not entirely sure of, but I'll show you in a moment how close it does get. Alright, I have 3 different rendezvous tolerances in seconds: 50 seconds, 5 seconds, 1 second. This the algorithm uses to slow the throttle down as I start getting close. I'm at full throttle till I get within 50 seconds of a future rendezvous, then I cut the throttle to 1/10 until I'm within 5 seconds of a rendezvous, then cut the throttle to 100th until I'm within 1 second of a rendezvous. This is the loop that does it. It's a simple doubly nested loop. This originally was a from loop that just says I goes from 0 to 4 and j goes from 0 to 4 inside of I. That's all this was, but I got a really weird error that a from loop nested in a from loop was throwing one of these C KOS devs error, and I just started noticing that like 2 days ago and haven't had a chance to analyze why it happened. But I know that when I took it out from being a from loop and made it a manual until loop that does the same thing, that problem disappeared. So that's slightly bothering to me because I can't reproduce it on a simple example case. I tried going back and making a GitHub issue about it, and so I tried making a tiny piece of code that just has 2 nested loops that does nothing more than print the numbers, and that worked fine. So whatever I'm doing in here is specifically triggering a bug, and I need to go analyze it later and find out what that is. So anyway, that's why you're looking at these kind of ugly looking until loops. This was originally a from loop. So this outer loop is I goes from 0 to 4, the inner loop is j goes from 0 to 4 inside of that. The outer loop is going to look at my rendezvous time now and in future orbits. So my period times I added on to when the first burn start is. So that's going to get all the multiples of my own orbit that comes back to here. I should do this in front of the camera. My own orbit that comes back to here, the next 5 of them. This is the same thing for my target. The next 5 times my target's orbit comes back to the same spot by doing very much the same check, only here I'm going to use the array that I built up above already. And all this is doing with these 2 nested loops is trying to find any match between these. Is there anywhere where one of mine hits one of theirs and they match within a certain time difference, within a certain rendezvous tolerance? So, are they within the first tolerance? Once they are, cut the throttle back a bit. Once they get within the second tolerance, cut the throttle back even more. Once they get within the final tolerance, then cut the throttle entirely. This is your found spot. And at that point it stops, remembers what I was, where it was within here, drops back out of that, and tells you, hey, I found a matching time. Now what it will do, remember this was all calculating on the fly while it was burning. Once it finds that it stops the burn, tells you how many orbits into the future it is, goes into this loop that again does something very similar to the one up above. I should probably make this a standard routine in a function, because I do this so many times, where I just in a loop wait and print out how long I'm waiting for, to just give you a visual idea of how long it'll be before you get to the spot. These values that it calculated that I kind of skipped over, what is the other's velocity going to be at the rendezvous time now that we've picked it? What will my velocity be at the rendezvous time now that I've picked it? Therefore, what is our expected delta v to match our velocities once we get there? It's just simply subtract the 2 vectors. And then finally, how much time ahead of that should I begin my burn to try to stop at the right spot. And again, that goes back to what I showed you on the page before. It's, oh! That's not right. Hey everybody, I found a bug while I was explaining it. That should be divided by 2. This is supposed to be half the burn time is when I start the time. I'm missing what people are saying in the chat over here. I've been talking to myself. Double up cooked control for a while using the cooked vector to drag myself to the target vector. Probably convert stuff to raw. Oh yeah, after they're doing target vector push shift vector. Okay, yeah. Yeah, raw steering is a good idea. I may do a future cast on how to do your own raw steering. Part of the reason I decided to make that not a topic of this particular one is because of the fact that I know we're about to flip one of those axes, and that's going to be a backward compatibility mess, and I don't want to say anything publicly that's going to get saved in a video that within a month or 2 becomes incorrect. So that's why I've sort of avoided the topic of cooked control, because I don't want to talk about it until after we get the axes flipped back to correct, so that I don't have to say it the wrong way. Okay, so we found it. Now you actually burn until relative velocity is killed. This is a very simple thing. I could have tried doing this with my burn vector I already made, but I didn't for reasons I can't quite remember now. And so I do something very similar to what I did up there, though, where I do this dot product to work out whether or not my relative velocity has hit an end. My relative velocity is simply my velocity minus the other's velocity. But here I'm taking out what portion of it is in the direction of my own facing. So again, I'm taking the component of it that matches my direction and ignoring anything that I might be slightly off from. So now I just burn in the anti-direction of the velocity difference between us. Leave the throttle on up until we're done. And again, I do a very similar thing that as I get near the end, I slow the throttle down for precision. And that's it. I will now show that in operation. And this time I'll remember to actually shift the picture. So now I will run the rendezvous. It says no intersect point in the orbits yet, which I showed you before is because it detected that we're not connecting. Waiting for Periapsis to correct this. It will make the burn to embiggen my orbit at Periapsis. So I can manually warp until I get near my Periapsis where the burn will occur. And there it dropped me out of warp because it detected it was getting close. And if you look, by the way, this is our awful cooked steering. Look at that. That needs work. And it's only dampening because I have SAS on. Okay, I will get myself closer to Periapsis here. It drops me out again, just to be sure. Oh, that's not why it dropped me out. This is actually technically in the atmosphere slightly. Whoops. Okay, there it is burning larger, 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 and then stops when we finally have intercepts. Just ever so slightly, my Periapsis was just barely in the atmosphere there. Well, that'll be fixed in a moment. It says it's going to wait 385 seconds for the next hit, which the predictor claims is here, which it claims is 6 minutes 5 seconds into the future. So where it is finding the hit is not the same place that the tracking center is finding it. It's slightly off. I'm not entirely sure why. Did I see you using an exponent? Yeah? Sure. Okay, anyway, so I warp to here. Slow down. I am within 20 seconds of when it will try to enlarge my orbit. 9, 8, 7, 6, 5, 4, 3, 2, 1. Enlarging, and here's the array of hits it's trying to find. It found one, even though it's not showing up here. It's slowing way down because it's getting near one, it thinks, and then it stopped. Oh yeah, KOS does exponents with a caret. Simple enough. Let's see what it found here. Now notice, it's finding a time by looking further into the future than even the stock game does. The stock game is not claiming we have an intercept coming up, because it's saying it's 2 orbits from now. And if you look up here, these are the times in universal timestamps when I'm going to cross this spot. These are the times when my target is going to cross the spot. And if you look right here, 463373, 0.1, 463373.8. That's the spot that it found where there's a match between the two. So, now I manually warp until my wait is over. He'll have a wait of 5,000 seconds because it's going to have to wait a full orbit. Now watch what happens as I get in closer here. As I cross this spot, this is the intercept that it found. That's the one it meant right here. And now it's saying 2,860 seconds in the future. That's basically one of my orbits. So I can zoom through there. And as we start getting closer, I will flip back out of map view. There we are. There is our target. As we got within 20 seconds, it changed to point retrograde relative to target, and you can see it wobbling all over the place until it settles in. Two, 1, 0. It burns. Here's my speed, slowing down, and then stops. And there we have it. It finished, and there I am, 0.2, or now it's 0.3 because I'm rotating. Weird thing everyone was talking about earlier. Now it's 0.4 because I'm rotating. Actually, not because I'm rotating, because I'm actually 3 kilometers away from it. No, it's not because I'm rotating. It's because I'm enough kilometers away that we're getting orbital mechanics maneuvering me around a bit. But there it stopped. It's originally stopped at 0.1 meters a second. It's getting a little worse as time goes on because I'm far away. But that is the script. Now notice I only got within 3 kilometers. It's not perfect. I think the reason this thing has so much torque, I didn't put torque on deliberately, but I have 2 capsules on here. I have the probe core and the one that you're going to put a crew member in. And I think it's the both of them together that are making it have that much torque. I could probably make it better if I right-clicked this and took that torque off. In fact, let me just do that. Let's just try how well that works. Let's lock steering to, oh, I don't know, up. And I'm doing this here without any SAS to help me. So I lock steering to ship up. It does its really pointless, stupid rotating it doesn't need to. Come on, when are you going to finish this? There, now it finally gets it vaguely under control. Nope, still working on it. When I tried writing my own PID controller once to try to rotate and fix attitude, I ran into a very similar situation to this, so I think it's doing something similar to something I did in my own KOS script once. Yeah, it's having a really hard time with this. What happens if I re-enable this? No? What happens if I put the SAS on again to get that rotating to stop? Interesting. Manual SAS is not working right now. I wonder if this is a different problem than I thought it was. I just disabled the torque on the pod. The torque up here is still present. But what I'm wondering here is, I've just turned SAS on. This is no longer doing anything with KOS. This should be stock. And it's not stopping. I wonder if unlocking the steering didn't really fully take KOS out of the picture. I wonder if it's still trying to do something. I don't believe that... Okay, well, it may very well be the case that this is actually just momentum rotation, but here's the point. I have SAS on. SAS should be stopping momentum rotation, and it's doing nothing. Off. On. Off. On. Off. On. Yeah, this is a different problem than axis coupling. This is, why isn't the main game doing anything with SAS right now? Why is it doing absolutely no effect? Alright, let me have a look then, HVAC. Give me just a second here. Okay, so you're saying that in my log, I should somewhere have... Nope, both torques aren't disabled. One is on. You're saying I should have something called... Actually, why don't I search from the bottom up? Oh, that's not supposed to be in the log anymore. I thought we took that out. Oh, that's right. I'm running on a debug version. Never mind. Toggle fly-by-wire. True. False. True. Yeah, okay, let's see. What was the last one? Toggle fly-by-wire. False. Okay, so that should have turned it off. I'm gonna attempt something really quickly here. If I go to the Space Center, and then reload the vessel again, aha, it stopped being a problem. That probably is a bug in KOS. We'll have to look at that. We'll have to examine this and figure out what happened. And of course, embarrassingly, everything we're talking about is on the open stream, so everyone will see this. But yeah, we probably definitely should be looking at the source and working out why that occurred and seeing if we can reproduce it again in the future. Because when I went to reload the scene, it stopped doing it. And I bet you now I can probably do lock steering to ship up. Wait a minute. Reaction disabled? Oh, they are both disabled. I'm both disabled. Never mind. Let's turn this one on. There we go. Now, that should very quickly point up and away from the planet, and it sort of is trying? Now, at this point, I think I wonder. Have you guys gone in over how to calculate pitch in a rendezvous? Nabisco, can you describe better what your question is? I don't fully get it. We actually just finished most of the discussion that, well, okay, discussion. I was talking. But at the end of it, I just did a little test and we discovered a thing that we think may be a bug in the code that we were trying to analyze whilst doing the stream. Well, yeah, but, okay, so let's say you've had problems with up, then. I think if I just pick any vector I feel like, I'll just make some vector at random here. Doesn't really matter which one. I think it's still the same problem. Hey, you know what it might be? You know what this might be? People have reported problems in the past with trying to use control from here, right? So people have done control from here on a part that's different from where it started, and whenever they do that, KOS's cooked steering gets all messed up. We've seen that bug report before and haven't figured out how. This is a vessel that I built from the beginning using the command pod here that's unmanned as the root part of the vessel. Then I stuck a computer core on top of it because I knew I was going to have the command pod be unmanned. So the pod isn't the root part. So could I be seeing the same effect as when you click on it and say control from here? Is this basically the same problem? I'm controlling from a part that isn't the root part of the vessel. And I can't control from the root part because the root part is the unmanned capsule. You can't control from there. So, for whoever's looking at the problem, I know that HVAC might have been looking into it. Look into if the problem is whether or not the vessel's concept of its root part location and its concept of the location it's being controlled from are in disagreement with each other. And that could be why it's messing up, because we're using two different ways of calculating the vessel's current position and orientation. Just a thought. Anyway, I'm not going to try to solve this here now. It's a different problem. I'm not sure what happened. But, Nabisco Fantastic, when we're done here and I shut this down, Twitch has the ability for me to turn the entire stream into a video and leave it up there as an episode for people to see, which I do intend to do. So, although you jumped in late and didn't see everything, it should be possible to view this entire thing as an episode later. I don't know how long it takes Twitch to get everything converted and put online. It's, you know, several hours, so it might take a while to get it ready, but if I've set everything up correctly, everything we've done for the last few hours should have been recorded. If it's not, I'm going to be really sad. Can I share the craft on Slack? Yeah, I'll get to it later. I'm thinking this episode on Twitch is getting kind of long, and we're starting to get into a bunch of developers of KOS talking to each other about interior issues. So I think we should probably shut that conversation down. Not that it's not important, but that the conversation about trying to debug the problem we can probably do together offline, or at least off Twitch. I'd like to ask Nabisco, who joined in at the last moment, if you have any questions you'd like us to address while we're still here at the tail end of this. I've got a few minutes. If you actually happen to have any Ask a Developer questions, you happen to be sitting right now conveniently in the middle of a chat that consists of several of us online together. I mean, you've got me, you've got HVAC, we're both developers in the mod, and you've got several people who are also developers who, you know, contributed smaller amounts of code and are also really useful users of it. So if you happen to want to spend this time on a couple of questions, this would be a really good time. Otherwise, I'm probably going to shut down the feed pretty soon here. Okay, well, anyway, I realize I rambled a bit. This was the first thing at doing this. I hope this is useful. I hope people find it helpful when the video is up and ready. And as to this problem, man, we've got to figure out what that is. It doesn't happen all the time. See, if it happened all the time, we'd be able to fix it because it would be easy to reproduce. Yeah, we're going to do more streams later. Yeah, debugging wasn't what I thought the purpose of this was going to end up being. My face is disappearing. What? Did this go off camera, you mean? Or is there something wrong? Oh, wow. Oh, sorry. The only reason my face disappeared is because I tiled the panels in the wrong layering order. There we go. That's better. Okay, well, yeah, Nabisco, if you have any suggestions on topics you would like to have covered, give the suggestion, because I want to do more of these, but I don't exactly know what topics would be nice, and having members of the user community say, hey, this is a thing I would really like to see an interactive discussion about, or an interactive tutorial about, then let me know, and I could try to make that the subject of the next one. Let's see. According to the time odometer, we've been on for 2 hours now. Oh, actually, yeah, 2 hours. I did say at the beginning that this could last 2 to 3 hours, so I'm not tired yet. If you want me to interactively do a thing now, I could even do it.